In this final short video, I'll describe why nearly everything in the universe can be a harmonic oscillator, provided it's not too excited. So we'll consider a particle that experiences a potential v of x and some damping. So here's some arbitrary v of x, and I've put the origin at this local minimum here. The equation of motion for a particle moving through this potential will be the force, which is equal to mass times acceleration, which is equal to the negative derivative of the potential minus gamma x dot. So I've included some damping here, negative gamma x dot, which is the form of the damping we've used in the previous couple of videos. We'll Taylor expand this potential into its 0, first, second, third order terms, where each of these b, c, and d are first, second, and third order spatial derivatives. We can now write the derivative, spatial derivative, v of x dx, by taking the derivative of this expansion. So we have b plus cx plus d on 2x squared, etc. Which, for small x, we throw out all the nonlinear terms, and we're left with b plus cx. Now we can recognize that b, in fact, must be equal to 0, because b is equal to the derivative about this turning point. That's 0. C must also be positive, because c is the second order derivative, and at a minimum, the second order derivative is positive. So let's substitute this solution back into our differential equation. This is our form of dv dx now. It's equal to c of x. This is where it appears in our differential equation. So change that into c times x, and we get back precisely the equation of motion that we've been dealing with the last couple of lectures, where c would be equal to omega naught squared. The consequence of that is that if you imagine a particle vibrating around this turning point here, provided vibrations are small enough so that this linearization approximation is valid, that motion will be described by simple harmonic motion. So anytime you see something that wiggles around a stable point, it has to be simple harmonic motion for small wiggles. This is a pretty universal phenomenon, and this is why simple harmonic motion is something you observe, at least in an approximate form, in a wide range of physical systems.